Welcome back. Today's lesson is section 8.2, the area of a surface of a revolution. What we're going to do is we learned in the last section about the arc length. We're going to take this arc length and rotate it around and creating surface. So let's look at this sample first. When we do the rotation, we get what's called a frustum of a cone. And so that's what this is here. And we can see the surface area is 2 pi times r plus r divided by 2 times the length. But what's easier to do is if I took the frustum and I cut it down, that's what this is here. I have a radius, and I unravel it, and I get this object here. It's just a rectangle, or basically a rectangle. And it's instead of the formula that we had up there, the surface area is going to be 2 times pi times r times h. Right? 2 times pi times r times h. So here's just what we're talking about. It says we want to rotate the above curve about the x-axis. So we're going to rotate it around this axis. Right? So we're going to end up with something that looks like this. Whoops. Something that looks like this. And just the surface area is what we're looking at. So here's a better depiction of it. And we say the surface area is 2 pi the radius. And the radius in this instance is from here to here, correct? And that would be the function itself times ds. And the ds is the arc length. So we want a surface area, 2 pi r, surface area, arc length, I mean. So this is the function we're going to use over and over and over again to solve these. And again, there's some really nice problems in this book that work out really good. So if I wanted to have this and I wanted to rotate, I'm going to create this function. And now, but this time it's x of g of y instead of x. So the rotation will look at this. Here's the surface area. So this time we're going to say we're going to rotate about the x-axis, right? Because this is all in terms of y, where the previous one, this was in terms of y. This one was all in terms of x. So now it's still 2 pi, but now it's y. If I'm going around the x-axis, if x-axis terms of y, use y for r. All right, so let's go back. All right, rotate about, this is the first one, about x-axis in terms of x, use function. So what we're saying is, if I'm the axis I'm rotating about, and I'm in that same terms, as in this instance, I'm using the function. The axis I'm rotating around is in terms of the other axis, the other variable. I'm going to just use that variable for my r. So now we're going to do the same thing. We're rotating around, and this time, all right, it's going to look like this big thing. This time, we're about the y-axis in terms of x. So that's why it's x, right? Because if we're not in terms of the same thing we're rotating around, then we use that variable. But if we do the exact same thing, now we're in terms of y going around the y-axis, it's going to be g of y, all right? So it's x when it's not around that same axis. So here we are. We've gone through quickly. It makes sense once we start working on this. And I'm going to talk about what we have. So I'm going to go about the x-axis, and I'm in terms of x. All right? So I'm going about the x-axis, and in terms of x. So let's go back. This is in terms of y. I'm about the x-axis in terms of x. It's 2 pi the function. Right? According to that, it's 2 pi the function. So we want a to be 2 pi f of x 1 plus dy dx squared dx. That's the function that we're going to use to solve this problem. So if y is equal to 4 minus x squared to the 1 half, y prime is equal to 1 half, right? 4 minus x squared, take that down by 1, multiplied by the derivative of the inside minus 2x. So y prime is equal to the 1 half times the minus 2x, gives me minus x out front, 4 minus x squared to the 1 half, which we could say is y prime is equal to minus x over 4 minus x squared to the 1 half. All right. So we need to know what y prime squared is. Well, y prime squared, square the top, I get an x squared, it's positive. The bottom is 4 minus x squared. 1 half times 2 is just 1, so it's just 4 minus x squared. So now we have the y, we have this part that we needed, right? So let's highlight it the same color, so we're not confused. So this is that part there. Our f of x is just this. So we have everything we need, and we know that we're in terms of here. So we have everything we need for this function. So I'm going from negative 2 to 2. Negative 2 to 2. I get 2 pi on the outside. My function, right, and our function is just this, 4 minus x squared times 1 plus dy dx squared. So again, we're just replacing, right, dy dx squared right here in yellow. So let's do the same colors. So here's my yellow, there's the purple, and there's the blue. So that's all my substitutions. So I'm going to clean things up because we don't want to do it this way. So I have 2 pi, integrate from negative 2 to 2. This on the outside is going to be left alone. I can write this all as one fraction. So instead of writing it as a 1, I can write it as 4 minus x squared over 4 minus x squared. And to that I'm adding x squared over 4 minus x squared. Now I can combine them. And what's interesting, the reason we did this is to clean up some of what we have, right? I now have the same denominator, and look at this. I can add them together. Now that I'm going to add them together, I have 2 pi, negative 2 to 2, 4 minus x squared, the square root of that. 4 minus x squared plus x squared just gives me a 4, all over 4 minus x squared dx. But what I'm going to do now is I'm going to break this apart. I'm going to write as 2 square roots. I do that so that I can see clearly what I'm going to cancel out. If I'm multiplying this together, this would cancel with that. And that gives me 2 pi from negative 2 to 2. Square root of 4, that's just 2 dx. I could rewrite that as 4 pi from negative 2 to 2 dx. It's a real hard, complicated integration, but I'll do it for you guys. From negative 2 to 2. I have to evaluate that, so it's 4 pi, 2, subtract the negative 2, which is 4 pi times 4, or 16 pi. So the surface area is 16 pi. Again, these aren't hard problems, you just have to be able to keep track. You know, if I'm rotating around the x-axis and I'm in terms of x, that's what this problem was, I use the function. If I'm rotating around the x-axis but I'm in terms of y, then I just use y. If I'm rotating around the y-axis and I'm in terms of y, I use the function. And if I'm rotating around the y function but I'm in terms of x, then I use y for my radius. So now we want to just set this up and do not evaluate because it's a little more complicated. So I have a y prime right? Because if y is equal to sine squared x, y prime is 2 sine x. So I take the 2 out front, reduce it to 1, so and I leave it alone. Then I take the derivative of sine, which is cosine of x. And then y prime squared is equal to 4 sine squared x cosine squared x. All right. So let's see. I'm going around the x-axis, and I'm in terms of x. I'm going to go from 0 to pi over 2. And this is the style. Since I'm doing this function, it's an a to b at 2 pi. 2 pi out here. All right. F of x times 1 plus dy dx quantity squared dx. So my f of x is just sine squared x times 1 plus my dy dx squared. 4 sine squared x cosine squared x dx. And that's my problem. I'm not supposed to evaluate it. I just wanted to get the answer. Get this over. So that's all I'm going to do for this problem. All right, so now I'm going about the y-axis. Oops, I'm going about the y-axis, and I have everything in terms of x. So let's see what we have. If y is equal to e to the x, right, then I could say, in terms of x, and so I need to look at my limits of integration, right? So what happens if y is 1 equal to e to the x, then x has to equal 0. So then I look at 2 is equal to e to the x. Right? I want to know what that is. Well, I can't tell you exactly what that is, but I could take the natural log of both sides. Natural log of on the left-hand side is 2. Natural log of e to the x is just x. So my x's look like they're arranged because I had to change my limits of integration from 0 to the natural log of 2. Right? So that's the range for that. So now I can say I have a 2 pi, and I'm going to keep everything here. So I have everything in terms of x, natural log of 2. Now I'm going around the y-axis, and I'm in terms of x. Well, that means I don't use the function. I use x times 1 plus, well, if y is equal to e to the x, y prime is equal to e to the x, and y prime squared is equal to e to the, what? 2x, correct. dx. That's 1. Now, let's just say we had everything here, so let's change colors. We already had y is equal to e to the x. 1 is less than or equal to y is less than or equal to 2. So in this problem, we have y. It's the same problem, but I have everything in terms of x, but I'm referencing y's. Well, can't I say the natural log of y is equal to x? So now my g of x is equal to natural log of y. So I have a function. So I could say x is equal to the natural log of y. All right, x prime is equal to 1 over y. And x prime squared is equal to 1 over y squared. So now I'm rotating about about y-axis. I didn't change what I was rotating around. I'm rotating about y-axis. I'm in terms of y, so then I use my function. I'm in terms of y, 1 to 2. My f of x is just the natural log of y, right? Because I'm using my function times 1 plus 1 over y squared dy. So hold on for a second. All right, welcome back. I took a second because I went into Wolfram Alpha, and I wanted to integrate them both to show you that I get the same answer. So this is the first problem. We did it from 0 to, well, it says log, common log. This one did it through the in terms of y, rotating over the same thing. Look, 2.86563, 2.86563. So I just wanted to show you that it doesn't matter which way we did it, that we get the exact same answer. So in other words, do what's easiest for you when you're doing these problems. The important thing was keeping it in rotating about what I was supposed to rotate about. All right, so here's another problem. Find the area of the surface obtained by rotating y is equal to 2x about the x-axis. So we're going by the x-axis. We're in terms of x. So 2 pi. Actually, let's find it. Y is equal to 2x. Y prime is equal to 2. Y prime squared is equal to 4. So I have 2 pi. I'm going to go from 0 to 5. If I'm going about the x-axis and I'm in terms of x, it's just the function, 2x. 1, whoops, sorry about that. Hold on for a second. Welcome back. Sorry about that. Technical difficulties. The file crashed. So we figured out what y is equal to y prime, y double prime. We said about the x-axis in terms of x. So I need a 2 pi. I'm going to go from 0 to 5. I need my function to the x times 1 plus my dy dx squared, which is 4 dx. So I have a 2 pi from 0 to 5, 2x square root of 5 dx. Well, it doesn't make sense to leave that out there, so why don't we bring this 2 square root of 5 pi from 0 to 5, 2x dx. So this, again, we're going to integrate this. 2 square root of 5 pi. The integration of 2x is just x from 0 to 5. So I have 2 square root of 5 pi times 5 minus 0, or 10 square root of 5 pi. Whoops. Ha, I forgot to write my square, which made me make a really dumb math calculation error. 5 squared is 25 minus 0. I apologize for that. 50 square root of 5 pi. That is the correct answer. Because I said the integration of 2x is x squared, and I just wrote x. So again, that's a very simple problem. There's not much to it. We only have a few more problems left. So, oh, and here's the answer in case you wanted to see it on the screen. So now I will find the surface, find the area of the surface obtained by rotating the curve. So we're in terms of y. We're in terms of y, but we're going around the x-axis. So if we're in terms of y going around the x-axis, my r then is equal to x. Oops, sorry. We're in terms of y. My r is equal to y. All right. So, but I still need to know what x prime is. So x prime is equal to, I had 3 halves, so that becomes 1 half y squared plus 2. Decrement that by 1. The derivative of the inside is 2y. Clean that up. X prime. 1 half times 2y is just y. Y squared plus 2 to the 1 half. I need to square that whole thing. So x prime squared is equal to y squared times y squared plus 2. Right, because this squared, this whole thing squared, well, we write it this way. I'm going to write this way so we can see cleanly what I just did. Y times y squared plus 2 to 1 half. All that's getting squared, and that's why I have y squared times y squared plus 2, which gets cleaned up to the y to the 4th plus 2y squared. All right, so let's write this up. I need a 2 pi on the outside. I'm integrating from 1 to 2. Because we're in terms of y, but going around the x-axis, our r is y times 1 plus dy dx squared. 4, oh, I can't read my own handwriting. That y looks like a 4 to me. Y to the 4th plus 2y squared dy. We can clean that up just so that we can see what we're doing a little better. We normally write our polynomials in descending order. Guess what? Perfect square trinomial. Perfect square trinomial is great because then I can factor. That becomes y squared plus 1 quantity squared dy. If I take the square root of something squared, I end up with 2 pi from 1 to 2 of y times y squared plus 1 dy. I can clean that up by distributing the y. 2 pi from 1 to 2 is y cubed plus y dy. Then I can integrate 2 pi y to the 4th over 4 plus y squared over 2. And I'm going to evaluate that from 1 to 2. And when I evaluate that, my answer, I'll let you do that on your own. My answer is 21 pi over 2. That's the answer after I've done my evaluation. So again, this was an example where I am in terms of y. I'm in terms of y, but I'm rotating around the x-axis, so my r value is not the function, it's actually y. See the next slide. So I'm in terms of x, I'm rotating around the y-axis, so my r is equal to x this time. I'm in terms of x, but I'm rotating around the y-axis. My r is x, it's not the function this time. So y prime is equal to minus 2x, and y prime squared is 4x squared. So I have 2 pi. I'm integrating from 0 to 1. My r value is x, because I'm in terms of x, but rotating around y. Again, I'm in terms of x, but rotating around y. So my r value is x. 1 plus my y prime squared is 4x squared dx. Now this one looks like I am a little difficult, but I can come in here and do a u substitution. U substitution saves us a lot of time, so I'm going to say let u equal 1 plus 4x squared. If that's the case, then du is equal to 8x dx. I have an x, but I don't have an 8, so I get 1/8 du is equal to x dx. So now I have a 2 pi. I need a 1/8. Integrate from 0 to 1 of x. Whoops, not x, because I just did a substitution, right? U to the 1/2 du. Pay attention to that. So I have pi over 4 from 0 to 1 of u to the 1/2 du. When I integrate that, I have a pi over 4. U to the 3/2, so I need a 2/3 here from 0 to 1. I can clean that up, and that becomes pi over 6 times u to the 3/2 from 0 to 1. Since I did not change my limits of integration, I need to go back and substitute for u. And u originally, we said u was equal to 1 plus 4x squared right there. So I have 1 plus 4x squared. 1 plus 4x squared to the 3/2 from 0 to 1. Now be careful, the assumption is you see a 0 and there's x's, you want to make everything 0, but it's not. So I have a pi over 6 times 1 plus 4 times 1 to the 3/2 minus 1 plus 4 times 0 squared to the 3/2. So I end up with a pi over 6. 1 plus 4 is 5 to the 3/2 minus 1 to the 3/2. I can't clean that up, so I will. Pi over 6. 5 to the 3/2 is just 5 square root of 5 minus 1. And that's my answer. That's the way I would prefer you to answer your problems. I would probably take 1/4 of a point off because you could simplify that. It's not very hard math. All right, let's look at another problem. So now I want the curve. I'm in terms of x, but I'm going around the y-axis. So what does that mean? I'm in terms of x. Oh, I'm sorry, I'm in terms of y. Boy, am I getting tired. I'm in terms of y. in terms of y about y-axis. So that means r is equal to my function, which in this case is 16 minus y squared. Square root of 16 minus y squared. So let's see, x is equal to this, which I could rewrite as 16 minus y squared to the 1/2. X prime then has to be equal, 1/2 comes up front, 16 minus y squared. Minus 1 from the half, I get minus a half. Take the derivative of the inside, minus 2y. Clean this up. I got 1/2 times the negative 2y, so I get y minus 16 minus y squared to the 1/2 negative. I could rewrite that as y, negative y over 16 minus y squared to the 1/2. That's only x prime. I need to know what x prime squared is. So I square everything. The minus y squared becomes y squared. And the denominator is just 16 minus y squared because it's a half. When I square the half, I get 1. So let's look at what I have. Well, actually, let's write the function. This is going to be an a to b of a g of x times 1 plus dx dy squared dy. Let's see what we have. This is this part here, and g of x, there it is. We want to go from a to b, which is in terms of y. So we have everything we need. Everything's in terms of y, so let's write this problem up. We need a 2 pi. I'm going to integrate from 0 to 2. Integrate from 0 to 2. G of x, 16 minus y squared, the square root of that. 1 plus, that's a y squared over 16 minus y squared dy. Now we want to clean this up like we normally do, so I'm going to rewrite what's under that big radical. Instead of 1, I'm going to write y squared. Oh, I'm not going to write that. Instead of 1, I'm going to write 16 minus y squared over 16 minus y squared. Now we have a common denominator, so I can add them together. All over y squared, 16 minus y squared dy. I'm going to clean this up. And again, these are steps I would like to see when you're doing this on your test, so I know what you're doing. When I combine it, 16 minus y squared plus y squared, I get 16 all over 16 minus y squared. Well, that's nice because that's another square root there. I can look at this when I multiply through. This would cancel with that one down there. This is dy. So I end up with 2 pi from 0 to 2, square root of 16 dy. Square root of 16 is 4, and I'm going to bring that out front. 8 pi, 0 to 2 dy. So now I'm going to integrate 8 pi. The derivative of the integration of dy is just y from 0 to 2. So I have an 8 pi, 2 minus 0, or 16 pi. So the surface area for this problem is just 16 pi. All right, we're going to keep going, see what we have left. So now what we're going to do is we're going to look to see what we have. These are the functions that we've been using and how they work. This is in terms of x, right? So this whole thing is in terms of x, this column is in terms of y. This is the row for going around the x-axis. This is the row for going around the y-axis. So let's talk about this. If I am in terms of x and I'm going around the x-axis, I use the function. But if I'm in terms of x and I'm going around the y function, I use x for my radius. If I'm in terms of y, but I'm going around the x-axis, I use y for the radius. If I am in terms of y, and I'm going around the y-axis, I use g of y. In other words, if I'm in terms of x and I'm going around the same axis that I'm in terms of, I use the function. If I'm not in the same terms as I'm in the same terms as the axis I'm going about, then I use the variable. Here's one more problem. I'm going to put on pause to make sure I have everything ready. All right, I just wanted to set up Wolfram Alpha. We're going to work out this problem real quick. And then we're going to use Wolfram Alpha to solve it. But we're not going to integrate this one. We're going to use a CAS, or a table of integrals. We're not going to use the table of integrals. That'll take too long. So we are looking at a problem where we're in terms of x going around the x-axis. So that means we use f of x. So r is equal to f of x. Y prime is equal to 1/2 x squared plus 1 minus a half, right? Because I take the 1/2 out front. I subtract 1 from the 1/2. That's where I get the minus 1 times the derivative of the inside, 2x. So y prime is equal to x times x squared plus 1. All right. So it's the minus 1/2, by the way, which is x over x squared plus 1 to the 1/2. I want to know what y prime squared is. So when I square it, I get x squared in the numerator. And the denominator is just x squared plus 1. So we're ready to set this up. Sorry, we're ready to set this up. So I'm going to go from 2, I'm at 2 pi. I'm integrating from 0 to 3. I want my r to be my f of x, which is x squared plus 1, times 1 plus my dy dx squared, which is x squared over x squared plus 1 dx. And again, we're using this formula here, in case we're not sure. A to b 2 pi f of x 1 plus dy dx 20 squared dx. That's the formula we're using to solve this. And we're using f of x because we're in terms of x going around the x-axis. So now that we have all this, let's go back over here. I took the time to already put this in Wolfram Alpha. So we're going to write the word integrate. We had 2 times pi times x squared plus 1 to the 1/2, or the square root of x squared plus 1, multiplied by 1 plus x squared divided by x squared plus 1, all raised to the 1/2. Or I'm going to evaluate that in terms of x. That's what this is for, from 0 to 3. So this should look exactly like what we would have wrote up. And this is the evaluation. So give me a second, and I will copy this down for us and put it on the notes. So now here is the answer. And that's what they got. Now let's go back in here for a second. That's the integration. And there's some other results, some other approximations, plus a constant. So here we are. Now this is a different answer because it came from a different system. It may have come from, we had used Maple or some other system at the time. Maybe just the answer that came out of the book. But I promise you that this answer here and that answer are equivalent. All right. I believe that's the last slide for this section. Thank you very much. If you have any questions, I will see you in class. Have a great day.